So hello everyone. So let's look at the simulation of the project plane strain forcing using ANSYS. So we will use a static structural simulations because we are assuming there are no vibrations on application of loads or by any other means. So we choose a static structurals. So here we have to firstly input the engineering data of the materials that we are going to use. So we are basically going to use annealed copper and we are going to use die steel. So for annealed copper we choose isotropic elasticity and as well as bilinear isotropic hardening. So Young's modulus of copper, if we look at it from the slides, it is 110 GPa and Poisson's ratio is 0.34. So Young's modulus is 110 GPa and it is 0.34. The yield strength is given as 33 megapascal and tangent modulus is 167 megapascal. So we can see this is the bilinear isotropic hardening. So this is the elastic part and this is the plastic part. As we can clearly see, the slope of plastic part is lesser than the slope of elastic part because Young's modulus is in gigapascal and the tangent modulus is in megapascal. So that is quite obvious. We now define for die steel. So die steel will majorly deform only in its elastic region. So only we choose isotropic elasticity, and we again set the Young's modulus to be 210 GPa and Poisson's ratio to be 0.27. Okay, that's fine. So the materials have been defined. So let us save it. So okay, the project has been saved. We now return to project. We now go to geometry to define the geometry of the material. Firstly, we choose the analysis type to be of 2D. Then we right click and we go to new design modular geometry. It's taking time. We click on new design modular geometry. It takes a little time. Okay, it has opened. So we choose XY plane and so we are now looking at XY plane right now. So we have to draw our geometry here. So we go to sketching and firstly we go to settings to make some grids here. We make 2D grids and we set major grid spacing to be 0.05 meter because the mesh width is 0.1 meter, so it is reasonable to set it like this. So units, you can check it from here. The units are meter and degrees, so it's fine. So we now go to draw. We choose rectangle because we are assuming it a 2D strain element. So we enlarge it a little so that these grids are visible. So this is the rectangle that we had drawn. So the width is 0.05 meter and the height is 0.1 meter. Each box has a height and width of 0.05 meter. We now make some dimensions on it. So let's give a vertical dimension to the given rectangle that has been made. and let's give horizontal dimension as well. Okay, so now we go to modeling. We expand xy plane and we see there is a sketch 1. We now want to create a surface from this sketch. Then we again select a sketch 1 and we click on apply. So on clicking on generate, a surface is created here, as we can see. Now we also need to make the dies, so the both the upper die and lower die. So we click on create new sketch. In sketch 2 we again go to sketching. We choose rectangle. So in case of die, the width is 0.1 meter and we can choose height anything. So let's choose it something. The height really does not matter because we are applying force from above the die, and so the height of the die does not matter. Now coming to the modeling part again. So we have to create the surface again from the sketch. Choose the sketch 2, click on apply, but we have to take care that we have to now change this operation as add frozen, because if it is add material, then what ANSYS does is that we have made two different blocks. It will think it of as the same body and it will combine it, but we want them to be different and we want frictional effects between them, so we have to change the operation as add frozen here. Then we have to click on generate to generate the surface. It has been generated again, and now we need another sketch for the lower die. Similarly, we again go to sketching, we again choose rectangle, and so this is the lower die. Similarly, so we again come to modeling, we choose a sketch 3, we again go to create surface from the sketch. So let sketch 3, we apply. Again we have to modify the operation to be add frozen, because we don't want it to be clubbed with the this copper block. We don't want ANSYS to treat it whole as a single body, rather we want it to treat it as three different bodies joined together, three different bodies which are in contact with each other, not joined. So we click on generate to generate the surface. So it has been generated. So this is our geometry that we will be using for the analysis. uh, right now let's also put a horizontal dimension here. So go to sketch 2. Okay, it's fine. So this is the preview of the geometry. Let's save this. It has been saved, we can exit it now. Now here in geometry we have to change the analysis type as 2D, not as 3D. We want to do 2D analysis. Okay, it has been changed. Now we go for the modeling process. It takes a little time to open again. Okay, so the geometry has come here. Now let's see the geometry. So we have three different surface bodies. So this surface body, let's rename this. So let's call it as copper block. Let's rename this as well, and let's call it upper die. Let's rename this and let's call it lower die. So for the copper block, we see here the details, and it is the material is structural steel, which we don't need. It should be annual copper. We change it accordingly here. Similarly, for the upper die, we want the material to be die steel. So again, we have to change the material. And similarly, for the lower die, we again change the material to be die steel. Okay, it has been done. So let's save it. Again, it takes a little time. Okay, so as we all know, we have taken only one of the part. So this is the symmetry line, and the copper block is like this. and the dies were also completely rectangular. So we had cut it symmetrically in the vertical direction. So we have to make this particular edge as symmetry line. So for this, we insert symmetry in it. We insert symmetry region, and in that, in geometry, we select it through an edge. So we click on apply. So as we can see, the symmetry normal is x-axis, so it is fine. The symmetry is along the y-axis. Now we come to connections. So there are two contacts. So there is a first contact between the die and the copper block, and in definition, the type has been defined as a bonded contact, but that is not true anyhow. It will be frictional contact, because in forging, friction plays a very important role, and the friction coefficient would be 0.05. Similarly, for the contact region 2 again, it will be okay. It will be frictional contact, and friction coefficient would be 0.05. Okay, it has also been done. We now come to structurals, static structurals. So the environment temperature is 22 degrees Celsius, means this experiment is performed at the room temperature. So there are, we assume there are no thermal effects, considerable thermal effects in forging. In analysis settings, okay, we have to turn this large deflection as on, because here we are going to do 25% deflection. So 25% deformation is going to happen. So that is actually large deflection. So we have to turn it on. Now let's try to do the meshing. So for that, we click on solve. So this is the meshing that is automatically generated. But what actually happens while doing finite element analysis is that at each of the node, an artificial spring is assumed, and the problem is solved accordingly. So it is a better practice if two elements are in contact with each other, the mesh lines should coincide, means should be in a single line with each other. But here it is not the case. So we can try solving it as well. Also, it has linear, means the lines are linear. We want it to be quadratic. So in mesh, we choose the element order to be quadratic rather than the linear or program controlled, and we set element size to be, let's say, 0.0025 meter, and we again do the meshing. So yeah, this is a good meshing that we obtain. So the lines are actually in a single line in all the three bodies, and it is a quadratic, the element order is quadratic as well. So it is a still solving. Okay, it is ready. Now let's insert a remote displacement for the bottom part, and we apply it. So the bottom part will not move, as we all know. So the x component will be ramped and it will be 0. The y component again will be 0. There will be no displacement in the y component as well. So all the 3 degrees of freedom will be 0, 0, 0. So it's also constant. Now let's apply a pressure at the top of the die. So we are actually trying to verify the problem. If a pressure of 86 megapascal is applied, we were getting a deformation of 25% according to theory. So we will try to apply a pressure of 86 megapascal, and we will try to see what deformation do we get here. So, so where do we need to apply the pressure? That is the geometry that we have to select. So we will be applying the pressure on the top die. So we select it and we click on apply. And uh, how will we define? So we will define it the pressure by components, and the x component would be 0, and the y component would be 88.26. So it is in the negative y axis. So it is minus 86. So let's see what was the pressure that is needed. So the pressure was coming out to be 86.62 megapascal. So we will apply 86 megapascal approximately. Apply minus 86 megapascal. That has been done. Now in solution we need to insert, we are mainly interested in directional deformation in the y-axis. So we choose y-axis here. We are also interested in von Mises strain, that is equivalent strain. We are also interested in normal strain in the y-axis, in y-axis direction. We are also interested in stress. So firstly equivalent von Mises stress. We are also interested in normal stress in the y direction. So these are the things in which we are interested, and we will be solving it for them. Okay, let's try to get a reaction force at the bottom point as well. So force reaction. So boundary condition is this, and is remote displacement. So now let's try to solve the problem and see what we get. So we click on solve. Now here we can get the solution information very well here. So here is the log that ANSYS prints. If we want to see the force convergence graph, we can also see it from here. So as we note here, whenever the sub-step converges, the force criterion also converges. That is one thing that can be noted here. And there are some bisections also that happen here, like this one. This is a bisection. So when it finds difficult to solve any problem due to increment in load or anything else, it just bisects it in half and then tries to solve the problem in two iterations. So this is how it does. So it is still solving, and 87% has been solved. Okay, so the solutions have been done. So let's look at the directional deformation. Yeah, this is the directional deformation. We see the barreling effect as well. And again, we see the maximum compressive strain just below the top die. That is what we expected. And the maximum deformation comes out to be 0.037. So actually we predicted it to be 0.025. So we are getting an error of 0.05. That is actually good. Then equivalent elastic strain. The variation is something like this. Normal elastic strain varies something like this. So this is the variation of equivalent stress. This is the variation of normal stress in the body, and this is the direction of reaction force that acts. So it's actually 8.7 and 8.7 meganewton. So if we calculate the pressure, so again it is 87.6 megapascal that is acting here. So in this whole example, the thickness of the workpiece was considered to be 1 meter. So again, if you look at some of the analysis, so the strain is more in the die where it is pressing it. So maximum strain occurs here. And if you look at the equivalent elastic strain, so it is least in the bottommost die at the right part, because we expect it to be here. And again, at the top die at the rightmost part, the elastic strain is quite low, and we expected the same. So thank you. That's it.